This video is entitled The Chain Rule. More specifically, the chain rule for derivatives. Alright, so let's take a look at a basic derivative, of course, of y equals x to the fourth and y prime equals 4x cubed. So let's say suppose that we had y equals 3x plus 2 squared. Well, it seems like we could take, bring the 2 down and then go 3x plus 2 to the first and be done with it. Which you could, because it's the first power, you could distribute that and make it 6x plus 4. So it seemed like that would be the answer. Now, but let me show you what really is the answer and what's wrong with this logic right here. So what I did was squared out that binomial. It's not 9x squared plus 4. You have to FOIL it out because you got 12x in there. So that multiplies out to be 9x squared plus 12x plus 4. Then if you take the derivative of that, y prime will equal 18x plus 12. So, and that's what Maple has. So there's a good chance that's probably right. Now, as I was saying about using a power rule, here's what I was doing, wrote up there a minute ago. I would just have 2 times 3x plus 2, which is 6x plus 4. It would then need a multiple of 3 to get to that 18x plus 12. So it's missing the 3. So in a face-to-face class at this point, I would ask, where do you think that 3 is coming from? So I'll pause for a second. Sometimes people will say it's the coefficient of x. That's not really correct. It is in this case only because it's the derivative of what's on the inside here. The derivative of all that, of 3x plus 2, is 3. That's where this is coming from. Basically, this section with chain rules, we're taking derivatives of composite functions. You may remember that from algebra where you had like f of g of x, like that. An inside function. Yeah, so we're basically doing this. So it's a little bit different technique if it's just x in there, than it is with another function buried in there. So in this case, you would have, let me make sure I haven't already written that down there somewhere. All right, well, I have for another example, so I'll wait till we get to it. How to represent this original function in chain rule form, composite form. So I'll just wait till we get there. So also here's what we're trying to evaluate over here, g of x raised to the n. Now you might think, well, why did we even need the chain rule if we can multiply that out? Well, suppose this exponent was raised to the 10th power, not the squared power. I wouldn't want to multiply that out. You certainly would have to use it for this radical. You can't break that radical up. That's impossible. Technically, I guess for this sine of 7x plus 2, you could use the expansion rule for sine of x plus y, but I still wouldn't do it that way. And that's why I said should use chain rule for these, even though you could get away without using it. But just assume that you will. Now this, I just put this drawing in there. It's not very helpful to me. Maybe if I was a little more mechanically oriented, it might make sense. But the definition makes sense to me. But this is weird. So if you find that useful, by all means. So you turn in one, and that gear turns the other axle, so forth, so on. Okay, I give up on that. All right. So if y equals f of u is a differentiable function of u, I often talk about f of u there, I wonder if they're sending us a message. But anyway, and u equals g of x is a differentiable function of x, then y equals f of g of x, meaning that the u equals the u is the g of x right here. So we're basically finding the derivative of fu. Well, there's two ways, and we're going to see a little more direct way to do this. This is more the formal chain rule method, but we're going to have what's called a general power rule here in a second. I show some examples using this chain rule method, but it's for other things, but it's not imperative that you have to do it that way. But this is true. But it's basically saying that dy dx would be dy du, in other words, derivative of y with respect to u, and then times du dx. Now, technically, these du's don't cancel algebraically, but they do visually. If you look at it, you see they're kind of would cancel visually, and it's left with dy dx. And the chain rule could theoretically carry on. I think we'll do one here in a little while where there's another little link to the chain, but I don't want to get too ridiculous on extending this out and making it too complicated. Now this can be a little tricky to understand too till we see some examples. So there's the saying that d dx of f of g of x means you take the derivative of f prime, and then the last part is the g prime of x, meaning the derivative of the inside. That's the way I'm going to sort of explain it is, don't forget the derivative of the inside. That's what happens right up here. See that 3, that's the g prime of x. It's the derivative of the inside part. Okay. Oh, that's the most important thing about the chain rules, always remembering to do that. So here's a little simpler way to write it then. That means d dx of f of u would just be f prime of u times the derivative of whatever u is, u being the inside part with respect to x. It's just less messy notation than this definition right here. The main thing is with practice, you'll get used to how to do these things where you don't have to specifically memorize or know the notation aspect of it. You'll be able to take the derivative as a process and not have to worry about all that. So that just comes with practice. So okay, I'm also writing the chain rule the first way they gave it right here. So if we take this 3x plus 2, but now raise it to the 10th power. So if you let u be 3x plus 2 to define the inside, y would equal u to the 10th. And then you take the derivative of that. You take dy du, which is 10u to the 9th, the derivative of y with respect to u, variable u, 10y to the 9th, and then the derivative of u with respect to x. The derivative of 3x plus 2 would be 3. So then you would multiply the 3 and the 10 to get 30. And then at the very end, you have to replace the u with what it's defined as. So always, your final answer must always be in terms of the original variable. So it's 30 times 3x plus 2 to the 9th. And Maple likes that. So that's good. Now this definition of the general power rule and I'll just kind of jump down to the second part of this right here. The general power rule says if you're taking the derivative of u to the n versus just x to the n, we've already seen the regular power rule, but once again, u means it's some sort of function of x other than just x itself. That's the idea. You bring the n down, you subtract 1 from the exponent, but you take the derivative of that u. That's very, very important that we remember to do that. That's the key thing on this chain rule. So without writing all that dy, du, du, dx business I did up here, so to take the derivative of 3x plus 2 to the 10th, you can bring the 10 down, like I did right there, change that to 9, and then the derivative of the inside, that's the way I always phrase it, the derivative of the inside, which is the derivative of the u, it would be 3. And then, I don't worry about oversimplifying, but I always like to combine loose terms like that. And I suspect on whether it's quiz or an exam in multiple choice format, I'm sure they would probably have the 3 and the 10 multiplied together. I guess technically if it was handwritten and you didn't do that, it would still be okay. Yeah, I'll give us a flag of approval here. Alrighty, so let's take a look at this. See, the chain rule could extend, but look at how, depends on, like I said, but notice I have dy dx, but notice that, so I have dy du, du dw, and then dw dx. Even though they don't cancel, notice how they line up. The du's line up, the dw's line up in such a way that you're left with dy dx. That's how you would know if you set up your chain rule notation appropriately, if you did it that way, is that they theoretically or visually cancel versus actually canceling. All right. Let's just try some more of these. Y equals 4x squared plus 8 to the 7th. Bring the 7 down. Leave the inside alone. Every once in a while I'll see somebody jump the gun and they're so focused on the derivative of the inside part, they'll do it right here with that exponent still there, and that's completely wrong. Bring the 7 down, leave the inside alone for a minute, drop the exponent down by 1, then tack on the derivative of the inside at the end. Don't jump the gun. And then you can multiply the 7 times 8x to get 56x. So the derivative of y prime would equal 56x times 4x squared plus 8, all raised to the 6th. All right, radicals, no problem. Just rewrite this radical as the 1/3 power, and then use the general power rule. Bring down the 1/3. Leave the inside alone. Subtract 1 from the exponent to get negative 2/3. Then take the derivative of the inside. Derivative of the inside would be 2x minus 3. And there you have it. So it's important to leave the parentheses there. Sometimes I'll see people do, and here's a Stewie says here, it's very important. I'll see people distribute this coefficient through this part right here with that exponent. You can't do that. That's algebraically wrong. Now, mathematically, you could take the 1/3 and multiply it by 2x minus 3. I'm not saying you have to do that, but you could, because that's to the first power. But you cannot use distributive property if that exponent is anything other than 1. The only time you can distribute is when that's to the first power. So I've seen people mess up problems by doing that. So we don't want to do that. So let's don't make that mistake. But even then, I wouldn't think, but you could distribute the times at the end, 2x minus 3, but probably no point. So I'm always trying to make people aware, just don't make bad algebra mistakes. You know, that hurts a lot of people when they're trying to succeed in calculus, is because they need to refresh their algebra skills or improve or whatever the case may be. Oh, here's a little power rule. Bring the 1/2 down. Leave the inside alone. 1/2 minus 1 is negative 1/2. The derivative of the inside, the derivative of 2x cubed plus 1 would be 6x squared. Now this answer is fine right here, but I went ahead and took the 1/2 times the 6x squared and just made it 3x squared. So that doesn't mean this first answer is not correct. It is. That one I decided to tidy up and combine the two terms together. But notice what I did not do was I did not multiply the 1/2 through the inside of this parenthesis. Very important. Here's 1 over 4 minus 5t minus t squared. Now I'm also mentioning over here the quotient rule would apply here, but I wouldn't use it. Whenever there's a number in the numerator, even though you can use the quotient rule, I wouldn't. Because I think it's just easier if you do like these next two examples, you see what I do here. But hey, if you want to, knock yourself out, have a good time. But I wouldn't. So anyway, so if I'm not going to use the quotient rule, if I'm going to use this chain rule, I'm going to bring this denominator up to the top, and therefore the whole thing now has a negative 1 exponent. Because if the whole thing was, was positive 1 on the bottom, you don't see it, but it would look like that. Then you bring it up, it becomes negative 1, and general power rule. So when I say general, When I say general power rule is part of the chain rule. It's kind of all connected. So if I'm saying chain rule, I guess technically the chain rule is that dy dx equals dy du, d whatever. But the general power rule is a chain rule feature. So I may use those terms interchangeably a little bit, but don't let that bother you. Don't let that confuse you. Bring down the negative 1 like I did right here. I left the inside alone. Negative 1 minus 1 is negative 2. And then I tacked on the derivative of the inside, which would be negative 5 minus 2t. Once again, I put the flag there, meaning that was correct, which I could have put the flag over here too. But just for grins, I could not send the negative 1 through this parentheses. Cannot do it because of that exponent. But I sent the negative 1 through the parentheses on the far right and made both those terms positive. But like I said, didn't have to. But I like showing that just in case that's something you might encounter as a multiple choice issue there. So this one, yeah, I wouldn't do a quotient rule. I'd bring the t minus 2 to the fourth up and just make it t minus 2 to the negative 4. There's a negative on the outside, so just leave that with 3. So I have negative 3. Bring down the negative 4. Negative 4 times negative 3 is 12. Subtract 1. Negative 4 minus 1 is negative 5. And then I wrote this here, which mathematically it doesn't have to be there, but I want students to see that I did not forget about the chain rule. I guess you would get lucky on this one if you did, but I would not plan on luck because, yeah, anytime the derivative of the inside is 1, I guess if you forgot, but let's don't forget just to be on the safe side here. But that's why I wanted to label it, and then I did not put it in my final answer. All right, let's look at trig derivatives. These can get a little tricky. Got to be real careful with some of these. And you'll see what I mean. Not just these definitions I'm talking about, just how we use them. Because sometimes you're going to see the chain rule is going to involve like this, where the u is the argument, but yet sometimes the trig function itself might be used. So it can be a little sneaky. It takes a little practice to kind of get this down. You can do it with work, no problem. Well, now we have all 6 derivatives listed here, as they were before that we've already learned. But notice every one of these now, so when these were just x's, they didn't have this u prime at the end of it. That's the only difference. Now they have the u prime, meaning you have to tack on the derivative of whatever that u is. Now this rule would have also applied to those other derivative forms, but because the derivative of x itself is just 1, we didn't need the u primes in there. So now we're assuming that u is something other than x, so therefore we'll have something there. So you have to be real careful on these because it's really easy to forget. Like this one is cosine of 10x. The derivative of that, so derivative of cosine is negative sine of 10x, but we must take the derivative of the 10x, the argument of the trig function that goes with it. So the derivative of 10x is negative 10. I mean, not negative 10, positive 10, but there's a negative already there in front, so it makes it negative 10. So the actual derivative of cosine of 10x is negative 10 sine of 10x. Because it's interesting when I teach like Cal 2 and Cal 3, if it's face-to-face, I'll maybe ask somebody real quick, okay, what's the derivative of cos of 10x? And a lot of times I'll get the response, negative sine of 10x, and they'll forget that 10. So if we get out of that habit early, that'd be good throughout your calculus career. It's an easy mistake to make, but it'd be nice if we didn't. That'd be good. The derivative of sine of 3x squared. Okay, well, it's going to start out as cos of 3x squared. That's certainly part of the answer, but we must also take the derivative of the 3x squared, which would be 6x. I tend to write these in front because that's the way most time answers would look. It's not mathematically wrong to put times 6x at the end. That's okay. But the way you would be recognizing answers would be with the 6x in front. So I figure I might as well write it that way. All right. So how about the next one? Tan of x cubed. No problem. It'll be sec squared of x cubed times the derivative of x cubed, which will be 3x squared. So the derivative of tan of x cubed would be 3x squared sec squared x cubed. Now we have cotangent of the square root of x. Derivative of cotangent is negative cosecant squared. So it's going to be, and I rewrote that as x to the 1/2, which is fine mathematically. So it's negative cosecant squared of x to the 1/2 times the derivative of x to the 1/2, which will be negative cosecant squared x to the 1/2 times the derivative of this, which will be 1/2 x to the negative 1/2. So there's, lots of correct ways to write this answer. This is one correct way. If it's multiple choice, you might have to, the answers might be back in radical form. I don't think that's, mathematically, it's not mandatory to put it back in square root form. On a written test, this answer I put the flag next to, I would love that answer. But this one, all I did was just, well, not only did I change it back to square root of x, but because it was negative exponent, I dropped it down to the bottom with the 2 negatives there, and then I just changed that back to the square root of x. So, all right, so that's just a different visual way to look at the same answer. Now, here's where it starts getting a little tricky. Sometimes the trig function itself will be u. So you just kind of have to look at it and then play around with it and see what kind of makes sense here, when you're looking at these. See, all these other, and this is going to be the case whenever the trig function is raised to a power, it's going to be the u. Now, if you have something other than x, that's when we kind of have a secondary chain rule process to this. The chain rule will extend one more step. But anyway, that's your clue. If the trig power is raised to the third. So I wrote it out like this, but then here's how you can really do it now. So if u is tan of x, we're basically looking at the derivative of u cubed. And the derivative of u cubed is 3u squared times u prime. So really you can treat this as sort of like a power rule here. General power rule. You bring the 3 down, you change that exponent to 2, and then you take the derivative of the inside, which in this case the inside is the tangent. The derivative of the tangent then would be sec squared. So it's 3 tan squared sec squared. Let me kind of show you here. Stewie's talking about the proper way to write, identify trig functions. When you identify a trig function raised to a power, these two forms are the correct way to do it. That's why both of these, even though they're different forms, are both correct. So I could have put the 2 right there above the n, made it tan squared, or I could have put parentheses around the secant. But this is correct. So if you put the 3 right there, or all in parentheses, and you put the 3 on the outside, that implies the trig function is raised to the power. It's not the same as this. When you see it written like this, that's saying the tan of x cubed, like it's written here with parentheses. That means the x is cubed and not the tan. So that's good to know. That's very important. Obviously, if you look at that and you're taking a derivative, you need to know which part's being raised to the third power. Now, of course, sometimes they could both be raised to the third power, but that's a different story. We'll talk about that. Like, oh, well, there it is. Ha! The next problem. Okay. Well, let's take a look at that. And this is one where I kind of call an extended use of the chain rule. We sort of have to do it one extra step here. So let's kind of, as long as we're careful, we're okay. So I kind of went, always treat the first step as the trig function raised to the power. We'll worry about the x cubed on the inside in a minute, but I mean, start out with it being like this, where u is tan of x cubed, yet it's cubed right here, that cubed. So I'll take the derivative of this first. So the derivative of u cubed would be 3u squared times u prime. So basically I have this. I have 3 tangent squared of x cubed times the tangent of x cubed, derivative of that. right there. So that stays as is. And the derivative of tan of x cubed will be sec squared x cubed, but then you got to take the derivative of the x cubed. So that's why I kind of call this a sort of secondary chain rule step here, because you have to take a derivative of the tan itself, and then you got to take the derivative of the x cubed. So it gets a little complex there. So the derivative of the x cubed becomes 3x squared, which I just combined the 3x squared with the 3 to make 9x squared, and then I have tan squared x cubed and sec squared x cubed. So now I use this with what the formal definition of chain rule versus the general power rule, which I've already mentioned that the general power rule is part of the chain rule. It's just its own specific situation. If you don't like this, don't worry about it. It's okay. You can do it the other way. That's fine. But I went ahead and did it this way, so I kind of gave it two little extra chain steps there where I let W be the x cubed, and I let U be tan of W, and then Y would equal U cubed. So if you try to envision because obviously the way I define this as a composite function, it's got to equal what I started with. So if you put W x cubed in here, you'll have tangent of x cubed. And then if I substitute that back into here, I'd have tan cubed x cubed. So that is correct. It would produce this original function. Yeah, so obviously if you didn't set this part up right, then the rest of it's not going to be right. So then the chain rule, starting with dy dx, would go dy du. So each time you take dy du, that means the u will be the new variable for the next step over here. Then times du with respect to w. Then that w, you come over here back to here, will be du dx. And notice how that lines up perfectly. In other words, dy du, the u's there, the w's there, so it's dy dx. You might like this way better, who knows? So if I take the y with respect to u, it'd be 3u squared. Then I take the derivative of u with respect to w would be sec squared w. And then the derivative of w with respect to x would be 3x squared. But you still have to substitute to get everything back into its original form. So w is x cubed, so that gives you a sec squared x cubed right here. And you have a 3, and make that 9. But you kind of have to do two steps here, because if u is tan of w, and you put w in there, u would be tangent of w cubed. So that's 3, and then tangent of w cubed squared. So see, that square comes from here, but you still have the x cubed here. So you have to substitute twice, because you have to finish in terms of the variable, the original variable, which was x. So it's just an alternative way. You don't have to like that. Hopefully you can get comfortable with one of those. Here's another one that's very similar. I did it both ways. This one, I'll just look at the first one real quick. Not worry about the second one. So it's 7 cotangent cubed of 3x squared. So what I would do is I wrote it like this, so you can see that that's what I call the inside part now. That's then raised to the third power. Makes it easier, I think, to visualize. Now you bring the 3 down. 3 times 7 makes 21. I subtract 1 from the exponent, makes it squared. And then I have to take the derivative of this, the derivative of cotangent 3x squared. So when I brought this down and made it a square, instead of leaving a square, which I could have done, I could have left the square out here. I don't know why. I just rewrote it like this. I put the square there. Based on what I was showing you in that other page about how you can place the exponent for the trig functions the proper way. There's 2 ways. Maybe I just didn't want to mess with the bracket anymore, but that's fine. They're both equivalent. And then I need the derivative of this. So this just drops down. So the derivative of cotangent is negative cosecant squared. So it's going to be negative cosecant squared of 3x squared times the derivative of 3x squared. So we got to take that derivative of that inside. So the first step This was the inside part to take the derivative of. Now that inside had its own inside, which is right here. So the derivative of that 3x squared produces a 6x. Right, so we have I just combined the 6x and the negative and the 21 and just put negative 126x way out in front and left it as cotangent squared, cosecant squared, 3x squared, and there we go. So this is about as complex as we're going to make these problems. So if you're worried about, oh no, is this going to get a million times worse? No, it's not. I think a double nested chain rule is about enough. All right, here's, and okay, see, I even made a note here on this one. That's sort of using the whole D something business there. If you want to learn it that way, you can, but we'll just come over here and look at this. I bring the 4 down. So it'd be 4 sine x to the 5th cubed times the derivative of sine x to the 5th, which would be cosine x to the 5th, and then times the derivative of x to the 5th, which that will be 5x to the 4th. So I combine the 5x4 with the 4. I just put a check mark there to indicate that technically that's correct right there. It means we've done all the derivative steps, but I just tidied up the 5 and the 4 and made it 20x to the 4th. That's all. But it was correct where the flag was. Now Maple, I don't like the way they distribute. It kind of contradicts the way that I talk about how you raise trig functions to powers, but that's okay. It's programmed correctly and everything's fine, but it's visually kind of contradicts what I say. It's this notation right here. When Maple does this, that 3 right there does mean that sine is cubed. It doesn't mean x fifth. That doesn't mean x to the 15th. I know I don't like that. Means this right here, the way I wrote it right there. I know, but fortunately you're not going to have to worry about the Maple or anything, but I want to at least mention that so you didn't look at that and kind of question that and wonder what happened there. But no, that is sine cubed, just the way the Maple does it. All right, let's play around with a few more of these. Probably got too many of these. That's okay. Kind of go through these a little quicker so we can maybe move on to something else. So that means this notation is secant of x squared. So the derivative of secant, you see I went ahead and copied it right here. You'll need to know these though. Be sec x squared tan x squared times the derivative of x squared, which I moved over to the front. Derivative of x squared is 2x. I'll put it in front. So it'd be 2x sec x squared tan x squared. I guess I could have put parentheses around the x squareds just to kind of clarify. But this one now the trig function is raised to the power. See, that's why I just did 2 examples: the arguments to the power, and now the trig function is raised to the power. So you bring down the 7, change the exponent for tangent to 6, then you take the derivative of the tangent right here. The derivative of tangent would be secant squared. So you have 7 tan 6x sec squared x. All right, here's another one that's a repeated application. I'm just going to kind of go through this one just real quick. Bring the 2 down, makes 10. The derivative of cosine of pi t would be negative sine of pi t. And then take the derivative of pi t. So the derivative of pi t would be pi. So it puts a pi out there with that 10. Actually, in this negative, the negative, the pi, and the 10 make negative 9 pi. Negative 10 pi cos of pi t sine of pi t. And looks like the alternative way, I decided to use a happy face there as a variable to brighten up our day a bit. So got a happy face there. And Same idea, and you'll end up with the same answer. I think I'll skip past this next one so we can get this moving a little bit. All right, here we go. Let's see, now we're finding the derivative at a point, and then we're going to say, while we're doing that, why not say, how about that tangent line? Sounds fun. So we're going to need the chain rule to take that derivative. All right, so you're going to rewrite that as raised to the 1/5 power. And then we would bring the 1/5 power down, subtract 1 from 1/5. That will give us -4/5 right there. And then we take the derivative of the inside, 9x squared plus 4. So now all we do is we're trying to find that slope, so the derivative, so we just plug the 2, and I circled which 2 it is. It's the x, not the y. The y just happens to be 2. So I'll plug it in there, and let's see what we got. Put the 2 in there, put the 2, put the 2. That's what our calculator's for. If I did it without it, that's okay. Anyway, it turned out being 1/2. That's kind of convenient. Well, that's mainly because the reason why it didn't turn out to be a radical is because this inside part here is 32, and the 5th root of 32 is 2. So that kind of made itself work out to where it wasn't going to be a radical answer. All right, suppose I wanted the tangent line. That would just be, there's our slope, y equals 1/2 x plus b. So we know that the x is 2 and the y is 2. So I put in 2 for x, put in 2 for y. That would solve for that. You get b equals 1. So that means the equation of the tangent line is y equals 1/2 x plus 1. So we come over here, and there's the point 2, 2. Somewhere right about there. And okay, that's a pretty good looking tangent line for that graph. I like it. Looks kind of right along there, so that's good. Now we have a problem that's combining both product rule and chain rule. So we start this off, obviously if you have a product or quotient rule, that's the primary application. And just any time that a particular term uses the chain rule, the power rule, then you will apply it. So you're always looking for, the product or quotient rule is always the starting point here. So here's the product rule, f prime g plus fg prime. So the derivative of x would be 1, leaves 3x minus 9 cubed. And then for the next part will be f, which is the x, times the derivative of 3x minus 9 cubed, which means you bring the 3 down right here. You would change that exponent to 2, and the derivative of 3x minus 9, the derivative of the inside, would be 3, where I wrote that out to the right. Right there. So I could tidy that up and make 3 times x be 9x. And just for grins, let's practice a little factoring here. Suppose we want to factor this and simplify it. They share a 3x minus 9 squared, so we can pull that out of there. And that would leave a 3x minus 9 right here to make it distribute to b cubed. And it would only leave a 9x right there. And you can combine the 9x and the 3x to make 12x. And I'm saying that's simplified enough. Yeah, you could factor a 3 out of here. And technically, you could factor out a 3 squared, though. You'd have to use the square there. So theoretically, you could actually get a 9 out of here and a 3 out of there for a 27 total. But Don't worry about that. Now I'm mentioning here is if we were trying to find horizontal tangent lines, that would be the instance we would need to simplify this, because if you're setting it equal to 0, you want it to be in as simple as form as possible for factoring purposes. Now, as I've done here, I set this equal to 0. You see the two factors set equal to 0. The square doesn't matter when you set something equal to 0, because if it equals 0, 0 squared, right, is still 0. Okie doke. So x equals 3 and x equals 3/4. So there's the 3/4. Got a horizontal tangent line, and there it is at 3. All right. Yeah, here's one that we would not simplify. It's pretty complex. But actually, I will show, well, we will. I'll tell you one thing we could do here. But let's just take the derivative first. So the primary starting point here is quotient rule. Then you can worry about any little individual chain rules as we go. So it's bottom, right here, times the derivative of the top. Now, this is a chain rule issue here. Real easy to make a mistake if you're not careful. The derivative of sine of 3x is cos 3x, but you must take the derivative of the 3x to make 3. Very important. Now you come over here, minus the f by itself, which is sine of 3x. Then we have to take the derivative of the denominator g. The derivative of x squared plus 4 to the 5th would be, bring the 5 down, change that exponent to 4, leave the inside alone, but then right outside here, take the derivative of the inside. The derivative of x squared plus 4 is 2x. Now, and we'll see this coming up in another example, but I might go ahead and explain it here first, because we're about to use it anyway. Let me just check ahead for a second here. Yeah. Now, we talked about in the quotient rule that, don't cancel these terms because they don't cancel because of that minus sign. Don't reduce them individually. However, someone could, because this one started out as a chain rule. What happened is, like I said, this wouldn't happen if this had not been to the 5th power. Had it been to the 1st power, what I'm about to do never would have happened. But anyway, you see that we have an x squared plus 4 to the 4th here over this side. So that means since you do have a shared term in the numerator, you could actually factor out what's the appropriate exponent term and then reduce it with a denominator. So let's say, for example, we had, bring up a new sheet here, where I'll use like a to the 5th, I'll just use a b. No, nothing there. Whatever there is just something we don't care about. And that was minus a to the 4th times some c we don't care about. Then I'll put an a to the 10th. So obviously this will apply to that same problem. Well, if you factor out, you can factor out an a to the 4th, and you would get a times b, because you'd have one a left over. No a's left over here. A to the 10. Now, once you've done that, we can do this. And change that to 6. Well, let me show you a quicker way to do this. It's mathematically correct, but it's a little faster. What I like to do if I ever had to simplify these is, all right, identify where the term with the lowest exponent is. Cancel it. Then that means take the other two exponents and subtract the exponent of the one you factored out. So 5 minus 4 would leave a 1, which obviously if it's a 1, you don't have to put a 1 there. And then 10 minus 4 would be 6. That's a lot faster. And then look at what's left, this answer versus what's left down there, right here. You would have a times b minus the c over a to the 6th. I like that. But we didn't worry about that for this one, so I don't know if that's going to be a big issue or not, but just in case. Never hurts to enhance our algebra skills. Now here's one that I said in its original form, do not simplify, but then we're going to take it one step further, and we are going to simplify it. So I'm going to obviously change that denominator and raise it to the 1/4 power. X plus 4 raised to the 1/4. And then FOIL that out. So we would have x plus 4 to the, what I say, I don't know what power I said. I hope I didn't say 1/4, but it's x plus 4 to the 1/2 power. Bottom times the derivative of the top is 1. No matter what I said, I do have it written correctly right there. Minus the top times the derivative of the bottom, 1/2. X to the 4th plus 4, subtract 1 makes it negative 1/2, times the derivative of the inside, which would be 4x cubed. And then on the bottom, it looks like I might have forgot to square it, but actually the square root of x to the 4th plus 4, the square root squared just kills the radical. So we just leave x to the 4 plus 4. All right, this is taking really long to do this, so maybe it's because I'm processing another video or something, but I'm going to pause this for a minute and see. And we're back. So you'd end up with this, and suppose we want to simplify this if we want to find the values of x that cause horizontal tangent lines. Now this is a little bit trickier with the negative exponents, but it still follows the rule that I explained for this one up here about where you could subtract 1 from the exponent, where I did this over in this scribble page there. That idea. That works here even with the negative exponent. So there's no doubt that the negative 1/2, that's the smallest exponent, so that's the term you cancel. But then you have to go 1/2 minus a negative 1/2. So you have to subtract that exponent as is. So 1/2 minus a negative 1/2 would just be 1 right there. And this cancels. Then on the bottom you have 1 minus a minus 1/2, which gives you 3/2. So you have x4 plus 4 to the first minus 2x4 over x4 plus 4 to the 3/2. And then x to the 4th minus 2x to the 4th makes a negative 1x to the 4th. So we have, 4 minus x to the 4th over that denominator. Remember we learned in the quotient rule section that when you're setting a fraction like this equal to 0, we only care about the numerator. The bottom doesn't matter. Four minus x to the 4th equals 0. X to the 4 equals 4. So always remember, anytime you have an even root, there'll be a plus and minus, not just squares. 4th root means there'll be a plus and minus answer. So kind of a weird answer, but that's okay. You have two values for x, plus and minus the fourth root of 4. All right. Fourth root of 4 is going to be 1 point something. So there's the two horizontal tangent lines of the graph at, plus and minus 1 point something, whatever that is. All right, let's find the equation of a tangent line at a point. That's an oldie but goodie. Done that one, but let's be careful. All we have to do is be careful with our derivative, and then the rest of the process is fine. So you bring the 2/3 down. 9 minus x squared to the negative 1/3. You take the derivative of the inside, which is negative 2x, right there. And then you don't really have, sometimes you saw me in problems combine those loose terms together, but, we're just going to plug a number in there. I wouldn't worry about it. You're sticking 1 in there anyway. So plug 1 in there as is. And obviously you can do this in a calculator. You don't have to do it this way. This one also works out because the cube root of 8 is 2. So it works out something that, like another problem we did earlier, the fifth root of 32 is 2. So it kind of works out non-radical based for this one, which is good. All right, but just put that in your calculator and come up with negative 2/3. So that means we know we're starting out with y equals negative 2/3 x plus b. Right here. So you see our points at 1 and 1, 4. So remember we've talked about other videos I've talked about where all they have to really give you is the x. You could plug 1 back into the original function here to get that 4 if you had to do it. But they gave it to us here. So you put the 1 in there for x, 4 for y. B is 14/3. And y equals negative 2/3 x plus 14/3. And there you go. That's it. So here's, now we're asking for the normal line. We did that before in another section. But that just means that all you have to do, you don't have to redo anything as far as your derivative. You just take that parallel slope, the tangent slope of negative 2/3, and you take the negative reciprocal of it. So that means the new slope we would use would be positive 3/2 from negative 2/3. Plug in the same numbers. There's not too much 1 for x, 4 for y. And once you have the tangent line done, it's not that much extra work to get the normal line done. And plug in 1 for x, 4 for y, I get 5/2. And that looks pretty good. You see the graph? There's my tangent line at the points 1, 4 right there. And have a nice tangent line. Running right beside it. I'm going to make that a different color there. So the red tangent line looks really good on that blue graph at that point. That looks good. And the normal line looks perpendicular visually. So I think we did a fine job there. Points. So this one's asking for points. So we talked about this before too. When it asks for points, you'll need to get your x. First out you find the x first, obviously. So then you plug it back into the original function and get the y, which isn't that much trouble. So now this one, I don't know why I chose to do a product rule here, maybe just to illustrate that. But I don't know, it would have been just fine to use the quotient rule. So I don't know what I did here. So if you wanted to try to, might be a good exercise for you then if you wanted to take this problem and work it via quotient rule. That would be good practice. And remember, all you care about is the numerator anyway. That's why I'm surprised I used the product rule here, because I would have just ignored the denominator. Well, anyway. So there's the product rule. So derivative x is 1, and then that stays the same. And then we have a negative 1/2 comes down. 2x minus 1 to the negative 3/2 times the derivative of the inside, which is 2. The 2's cancel. Because of this minus, that becomes subtraction. And I then factored out the smaller of the 2, which would be the negative 3/2. So that would leave a 2x minus 1 to the 1. You can check that real easily by adding the exponents. So 1 is right because negative 3/2 plus 1 is negative 1/2. In fact, that would always be a 1 because when you're taking the derivative, the part where you're taking the derivative right here, the power rule says you subtract 1. So therefore, that would make these exponents here always be a difference of 1. And then you're left with just here, the only thing left is x. So you combine that out, 2x minus x, you have x minus 1. So, which is what you would have gotten probably something, well, anyway, doesn't matter, but we'll just stay with this quotient rule. But so all you care about is the numerator. X minus 1 is 1. So x is 1. So you plug 1 back in there at the beginning, you're going to get 1. So the point's 1, 1. There's where I have the tangent line drawn. I'll put that little yellow fellow in there to represent the point. And there we go. Trig function. This one's always delightful because this can really test people how good their trig skills are, especially solving equations, which is one of the most important things in trig. I don't place a huge emphasis in graphing trig functions in calculus. I figure if we need to see a graph, I would let a calculator do it or something. So, but solving equations, that's a good skill to have. Well, okay, so we're going to find the points for the horizontal tangent on this one. So we have to take the derivative of this function. So the derivative of 2 cos of x would be negative 2 sine of x, plus the derivative of sine of 2x is 2 cosine of 2x. We must remember to take the derivative of that 2x. I'm really emphasizing that because I've just seen so many people that forget to do that. Like if I go, what's the derivative of sine of 2x? I'll go cos of 2x. And I'll go wrong, but close. It's 2 cos of 2x. Now, because we're going to have to, technically that's the derivative, but because we're going to have to get this into a form of solving it set equal to 0, we're going to have to use trig identities, which is, you can get this off the trig sheet that I provide. The trig derivatives aren't on there, but all these identities are. So, if this has a double angle like this one does, you want to make sure you convert it to one where it shares the same trig function as the other one here. In other words, this first one is sine of x. So you see this cosine of 2x, it's the same identity, but it can just be written in 3 ways. I chose the 1 minus 2 sine squared of x because I want to turn this into a quadratic equation involving sine. So I guess the point I was trying to say a minute ago and wasn't making clear even to myself, even though I knew what I was trying to say, was suppose this sine of x right here in front had been cosine. Then I would have wanted this to be cosine. So I would have used this middle one. There's really no need to use that top one here, but I would have used the middle one. I would have wanted everything to be in terms of cosine. So now we're turning into a quadratic equation. So you distribute the 2. I reorganize the terms. And then I went ahead and factored out a negative 2, so we're left with this. So actually, and these problems are generally set up this way. Certainly I would do it on an exam, but even this textbook's good about doing this. The last thing I'd want you to have to do is a quadratic formula with trig functions. That would be terrible. So I just sort of used a substitution method. I didn't want to use x, obviously, because x is our variable, so maybe I shouldn't have used y either, but because y is f of x, but okay, so please forgive that oversight. So I'm basically just letting y be sine of x just to make it look better here. So you set this equal to 0. So once this is set equal to 0, I didn't show the step here, but I'm going to mention it. That negative 2 goes away because if you divide both sides by negative 2, that's still going to be 0. And it leaves 2y squared plus y minus 1. And then that worked out to be factorable, which these, like I said a minute ago, these generally will be factorable. So it's 2y minus 1, y plus 1. Then you just go back. So if you replace sine of x with y, now we place it back in terms of sine of x. And notice this is between 0 and 2 pi, so we're not using the, infinite unit circle idea, and I don't like using that for this class. The 2k pi or the 2n pi business that you probably learned in trig. So some instructors might want to use that, but I don't. So I replace this, so I have 2 sine x minus 1 and sine x plus 1. Set those, when you have two things multiplied together equal to 0, remember the 0 product rule says you can set each factor equal to 0 individually. So you set that one equal to 0, you'll get sine of x equals 1/2. You set the other one equal to 0, you get sine of x equals negative 1. So I just go over here to the unit circle, and sine of x equals 1/2 is 2 locations, pi over 6 and 5 pi over 6. And sine of x would be at being negative 1 would be located at 3 pi over 2. So you have these three answers right here. Oh, it looks like that I said, okay, it says points here. So I probably wouldn't do this on a test with a trig function either. I probably just would stick with the values of x. Technically points, I should have plugged it back in. I don't think I did I? Okay, well, we'll just pretend like it just says the instructions say values of x only. But technically I should have plugged it back in. But I know I don't ask students that on a test, so therefore I don't do it. Not for trig functions, maybe for just regular numerical values. So those are your 3 x values that would give you horizontal tangents. You see the graph. I scaled it by pi over 6 because 6 is the common multiple between those three. Because that 3 pi over 2 would be the same as 9 pi over 6. So it's easier to see. You can count the units better, the x units better that way. So, and just like the way the last section ended, here's how we're going to end this section here with this idea. I just did B and D here, 102. So now it's telling us, giving us information, unlike the last section where we had all the information we needed. Here it's letting us know, hey, something might be missing. So you can, if something's missing, state what would be needed. So this is basically the chain rule without doing the dy dx, the basic concept of the chain rule, so the derivative of g of h of x, that goes back to the very beginning notation, is g prime of h of x times h prime of x. So that's the general. Let me just pop back up to the top for a second here and show you. That would be this right here. That's where that's coming from. Sort of the general format of the chain rule, or general power rule. I use those interchangeably. So let's see what we have here. So that means f prime of 5 would be g prime of h of 5 times h prime of 5. Well, up here we know that h of 5 is 3, so we're good right there. And then h prime of 5 is given as negative 2. So it would be g prime of 3 times negative 2. But we go back up here and we have a problem. We don't know what g prime of 3 is. It wasn't given to us. So without g prime of 3, we're stuck. That's the end of that problem. So like I said, that would be not possible. And then we stated what was needed. The next one is d. So you bring down the 3 exponent, change this to squared, and then the derivative of the inside. That's the general power rule for sure right here. So that means f prime of 5 would be 3 g of 5 squared times g prime of 5. So let's see if we have all the information we need for this one. G of 5 is negative 3. G prime of 5 is 6. So we're good here. So it's going to be 3 times negative 3 squared, and then times the 6. And then that turns out to be 162. So we had everything we needed for that one. And that concludes the video for the chain rule.